Yeah, now we have the second part of the introduction.
All right, yeah, thanks so much. That's nice to see a good number of people again. So, yeah, I wanted to first of all write down the table again of examples of Markov categories from last time. But now, because there's fewer boards and we haven't been able to enter the room earlier, I haven't been able to do that. But maybe I can just recall them briefly like this, right? So there was a Markov category for discrete probability that we call Finstock. There's one for general measure theoretic probability that we just call stock. Then I had suggested this time-dependent version called time stock, where an individual box like this represents an entire family of things that kind of unfold in time. So the time dependence is hidden under the hood. There's a Markov category for Gaussian probability. Then we had looked at these group things with symmetries. And then finally this maybe a bit more exotic example of unknown fun, which has no probability at all, but where the uncertainty is in unclarity about which functions from a given set of functions is the correct one, which one is actually implemented. And so where this box with each of these boxes denotes an entire conceivable set of functions that it might be. Yeah, and any more questions on that? And let's say on the definition of Markov category itself and on the structure of these objects, morphisms, tensor, and composition. Okay, yeah, then I will assume that that is more or less clear. So yeah, then the last thing that we had gotten to was the definition of conditionals, conditioning. And so here I've written it out again, that we say a Markov category has conditionals if for every morphism that has two outputs, we can factor it in this way into something that generates the first one first. So kind of looking at this part, and then as a function of the overall input and this first output, it generates the second output. Yeah, this is fundamentally somehow what conditioning is about and what enters, for example, in the fact that causal models are so, in the DAG sense, DAG causal models are so ubiquitous because there one makes the assumption that for every variable there is one thing that generates it, right? Namely, and if you take the factorization criterion as the definition, then for each variable there is only one thing, one conditional distributions that it's generated from, and there's nothing like two variables being generated at the same time, or I mean, don't mean time in a physical time sense, but kind of generated jointly by one conditional distribution, right? There's no such thing. And that is actually maybe also a question I would have for you. Is that actually, in practice, a reasonable assumption to make? Because I suppose there often are situations where one encounters some kind of happening, I don't know, maybe from a chemical or biological reaction, where it's the same process that generates several variables jointly, right? And then it seems a bit artificial to order. I mean, then of course we can always decompose it, because in discrete or measure theoretic probability this conditioning is possible. We can order them in either way we want, and that's basically making use of this property. But maybe that's actually a bit artificial, and maybe one shouldn't be doing that. What are people's thoughts on that?
Yes, I can think of one scenario in which maybe so like if you have a causal DAG, but you don't observe some of the variables, I think if you're trying to produce samples from the pure joint distribution without having to actually sample the unmeasured variables, I think in that case you do worry about sampling jointly, like the things that are all connected by the same unmeasured variable. You somehow have to come up with a way of sampling those things jointly given parents, but at least that's one. I know what Baldwin's worked on that, right? With Vanessa.
So that would be a situation where you do not want to, assume any particular,
I mean, you can always have vector variables for it, so you might not do that, but there's nothing to stop you doing it.
Yes, but that's not the same as it, because I mean then you might have other things happening in other places that only depend on one of them, and so you may still want to distinguish them, right? And I mean, I imagine a chemical reaction where it has two kinds of things that come out of it, and only one of them kind of, enters into something else. Yeah. Okay, I mean, this is just to say, basically, the main point I wanted to make is that when conditionals exist, then we can do this, and somehow seems to be an assumption behind causal modeling with DAGs, right, that this is possible.
Among the examples you give, which one doesn't have?
Yeah, right. So Finstock has conditionals. Stock is actually more subtle in that it has, well, if you consider all pathological measurable spaces, it doesn't, but the suitable restriction to standard Borel spaces, which are the ones of interest in practice, that's fine. Time stock, I'm actually not sure. Probably not. Gauss does. That's when you do that, you get things like the Kalman filter. I mean, the Kalman filter type equations are basically conditioning in Gauss. Yeah, the equivariant thing I think does as well. And unknown fun, I don't know.
I guess I forgot where this quote come from, but people say probability theory is fundamentally different from measure theory or real analysis because of this concept of conditioning and conditionals. So in some sense we're all
I can see that.
trained to kind of think about these things, so we think they're quite natural.
I mean, I would have thought that the difference is that one is just interested in different things, different questions about probability spaces. But maybe, yeah, right. I guess certainly we don't assume conditioning to be possible in measure theory in general. Okay, so now I was thinking we could talk about this causality axiom a bit more. After I had made, or I could directly proceed to conditional independence, and or say something about how the equivalence between DAG causal models and things like functional models can be generalized, or how that works in this picture. Okay, then yeah, I guess I can continue with the causality axiom, since I had made a mistake at a workshop of presenting that, and maybe somehow suggesting that it had anything to do with causality in the sense that we're talking about here, while I'm not really sure if it does. The real causality axiom in that sense would really be this one, as I've just tried to emphasize.
So to clarify, are you like endowing this with some causal interpretation here, or is this purely?
No, purely mathematical. But I mean, the causal interpretation, I guess, is helpful and provides helpful intuition, at least to me. Yeah. So including that here we have. Yeah, I'm not sure how to draw this as a DAG, but I mean, then I kind of would like to draw it like this. right, this A somehow generates X and Y jointly, and then on the right-hand side, we can also write this as a DAG, like this.
I think if you're talking just this kind of, in terms of presenting things, if you're presenting to statisticians, I think if you're going to say that in general a joint distribution can be decomposed in this way and that's causal, that's going to you're going to get a bad reaction.
No, sorry, I didn't mean to say this is causal, but
Yeah, I think if you said this is a factorization basically, or this is an ordered factorization, things like that.
What I mean is that this property is behind the mathematical structures that are used in causal inference. The fact that this is possible, that would be my.
But I mean, you're sort of implicitly assuming no confounding when you write that, right? So it's not just that. That might be necessary.
I mean, there is no sort of statement about causes.
So you're not claiming this is a causal DAG. This is like
Right. No, I'm just claiming this as a mathematical statement. Mathematical. I claim that this is behind the fact that this factorization is always possible, without additional confounding, is behind the mathematical structure of causal models and causal inference.
But, I mean, it's also just updating, right? Bayesian updating.
Yeah. Exactly. Yeah. Sure. Yes. Yeah. Mm-hmm.
Is there some like machinery for like introducing interventions or counterfactuals or this kind of thing?
Okay. I mean, there is a paper about this, which actually predates Markov categories somewhat, by two computer scientists who developed, and they called it string diagram surgery, where you then kind of cut a wire, and then you, let's say you could do it here. We just cut it here, so we discard this value, and we just put an extra little a here, so this will be intervening and putting a new value here that is, separate.
Well, I don't want to distract too much from your intended, but I am curious whether that sort of implies cross-world counterfactuals because of the way these boxes are.
Yes. So this I don't know. Yeah. But this is the sort of thing that I feel like one can now think about, but I haven't done that yet. Yeah. But I'd be interested in talking more about that. Okay, so the causality, what we call the causality axiom, for a reason that we can discuss, is the following statement. And again, this may or may not hold for a given Markov category if, and let me draw it in string diagrams first, and then I'll draw also a DAG version. And also I can write this equation down in a third way using almost sure equality. Okay, so the axiom says that if you have an equation like this, then automatically a stronger equation holds, namely one where we would also copy this value and use the value that kind of flows on this wire, as an intermediate, or as an additional overall output. H supposed to be A. Yeah, I mean, you can read it as L if you like, but I mean, yeah. Okay, so yeah, maybe let's discuss these equations a little bit, or make sure we understand them, and then draw a corresponding DAG version. So first of all, the equation on the right easily implies the one on the left, because you just basically discard. So we compose with the deletion morphism on the right here. So it means discard this thing, but copying and discarding just does nothing. So we can just erase this and just put an undecorated wire there. So the implication from right to left is kind of always true. And the axiom says that also the left to right implication should hold. Okay, and so yeah, we call this causal without any sort of, without thinking about causal inference at all. Because yeah, this in a sense, what this is doing is that here on the right-hand side, this is also looking at the correlation of what had happened in the past of G, so input to G. While on the left-hand side, it's not doing that. This is getting marginalized. And this is not an overall output. So what happens here has no bearing on whether this equation holds or not, if you want, because this does not become an output variable. So
is that H1 on the leftmost, and just having trouble?
Yes, yeah. So the equations are exactly the same with H1 here and H2 here, except that here we also this becomes an additional output. Okay, and so this is causal in just in the sense that kind of the choice between H1 and H2 in the future of G has no bearing on the past of G or on the correlation with the past of G. This was roughly the thinking that we had when calling this causality. Yeah.
This is an axiom that allows you to kind of get new wires. Is that?
Yes, exactly. Yeah.
I don't remember all the other axioms, but I guess they don't allow you to kind of
Right.
these.
Yes, exactly. But still, somehow this is so natural that maybe it's a bit surprising that this can be violated. But if you take, for example, Finstock, and suppose you modify it by allowing the probabilities to be negative, but you keep the normalization of probability, then this fails.
Could you just write down what is the Finstock statement that's equivalent to this?
Sure, yes. Okay. Then I suppose I should name these. So then, let me actually then maybe draw the DAG for the DAGs first also. So in terms of DAG, maybe on the right-hand side, this diagram can be directly translated into a DAG because, well, this is just a Markov chain. This generates x from A, y from x, z from y, and all. Well, A is a little different because A is an input variable, so it does not have a distribution itself. But the other ones are output variables, so these have a distribution depending on A. So this is kind of the causal structure that appears in this equation. And maybe I will denote overall input variables and by a box here just to keep track of that in the DAG as well, that A does not have a distribution. Okay, and so on the right-hand side here is just saying that the conditional distribution of Z given Y, we can use H1 or we can use H2, it's the same thing. And so this already also I suppose, presumably indicates or suggests that this is related to almost sure equality as well, because the conditional is unique up to almost sure equality, right? And this is saying H1 and H2 are kind of two different versions of this conditional.
So what's the corresponding DAG of the left-hand side?
Of what? Oh yeah, right. Yes. No. Let me get to that. Well, so as I said, this is exactly the same, except that x is not an output, but x is marginalized. So this means x is latent. So this is otherwise it's the same causal structure. So maybe I will use a circle for a latent variable. So this would be the DAG here. Right, so, yeah.
Can you just explain how H1 and H2 show up in the DAGs?
These are the conditional, well, they don't show up in the DAG because the DAG is just a statistical model. It's not any particular distribution, right? Or
maybe I'm not quite using the right terminology.
I think it's saying if you have two ways of generating z from y that are giving you the same distribution, then
Okay, I see.
yes. So suppose that the distribution is the same when x is latent, then it's also the same when x is observed. That's what it says, and this happens to be true in, say, most of the Markov categories I've mentioned. Or maybe even all of them. I'm not quite sure about unknown fun in particular. But yeah, it should hold in all the others.
You're saying when the probability coming negative doesn't.
Then it doesn't hold, right? Yeah. Sorry. I mean, by saying it holds in all the examples, I meant the ones from the table. But with negative probabilities, it fails. Yeah.
So is that a distinct Markov category that allows for negative probability?
So the one where you just take usual discrete probability, which we call Finstock, and you just allow these probabilities to be negative. So it's a variation on Finstock.
why is that? Does this fail in that case? Is it obvious?
No, it's not obvious. It's just have to kind of write down a concrete example. But the next thing I want to do is to actually prove fully at the categorical level that the existence of conditionals implies that a causality axiom holds. So these two axioms are not independent, but the one implies the other.
What would it mean for this to fail? Like marginalizing out the x destroys exchangeability of H1 to H2? Something like this?
No, more like the other way around. It can give you additional exchangeabilities, right? You may have more freedom of it. So if it fails, that means that this is true, but this is not, right? So there would be H1 and H2 that are exchangeable when x is latent, but not when x is observed.
So in other words, observing more cannot destroy your exchangeability.
Yes, that's also a nice way to put it. Yeah, right. Where not, I mean, exchangeability not in the definitive sense, but yeah, in the sense of replacing the causal mechanism by another.
So is the term like causal because there's some notion of like the future not affecting the present or something? Okay, but this isn't really like a temporal ordering, right?
I guess that how broadly is your notion of, how broad is your concept of temporal?
Well, like these could be measured at subsequent time points, and you can rearrange, right?
Yeah. I mean, there is still a kind of linear order in these causal structures, right? So in that sense, I guess it's temporal.
But well, I'm not isn't this Markov equivalent to going z y x a? the other way around.
Right, yeah.
So in that sense,
Except no, here A should be an input variable.
okay.
With the negative probabilities, so that is that category things still have to sum to 1 or not?
Yes, they do.
And is it partly that with negative probabilities you can make things cancel so it looks like you're, I don't know, in some sense so it looks as if you've got the...
That's a good point. I don't remember if that was the reason or not. Yeah, maybe. Yes, actually, yes, I think so. I mean, that is kind of why conditionals don't exist if you have negative probabilities, because you can get 0 more frequently. and so that also must be the reason. Yeah. Okay, but so Thomas suggested to write it down in Finstock. So yeah, okay. All right, so now here's the first kind of categorical theorem and proof to see how we actually reason within this framework. So every Markov category with conditionals is causal. Yeah, and the proof is kind of in the direction of what Caleb had already suggested, of just reordering the variables using Markov equivalence. At least that's kind of one way how one can think about the proof. Yeah, so I'm assuming the left equation now, right? And in terms of the left equation, I will prove the right-hand one. So let's write down the right-hand equation, or at least the one side of it. Oh, well, doesn't matter which one. Okay, and now I want to use the fact that we have conditionals in our category. So, and the way that I want to do that is that I want to look at this subdiagram. So this is kind of looking at a x and y only. And here I kind of want to do, well, I guess we could call it Bayesian inversion, or just use Markov equivalence. So apply the existence of, no, sorry, I drew this a little too far up. This should be before the copy here. So the idea is to consider the red subdiagram as a morphism to which we can apply the axiom. And so kind of rewrite it the other way around. So this means that there are going to be, or that there is going to be some morphism S, which is the conditional, such that we got the thing in this form. So yeah, the what corresponds to the F up here is this part, because so it's precisely the red thing here with the second output marginalized. So this is just F followed by G. And then this S is the actual conditional. Sorry, and now I still forgot this extra copy here. So this goes here.
So to combine kind of F and G in a single box when you apply this conditional axiom?
I just, yes, exactly. Yeah. I mean, I can apply the existence of conditionals to any morphism and any subdiagram that kind of has no holes or something where I can just compose those things to one morphism, right, and consider it as a single morphism.
Okay. That's one of in the axioms introduced already.
Kind of implicitly, yeah, because this applies to every morphism, and I can compose morphisms using string diagrams, so that's how it applies. Okay, and yeah, in a way, in some way, this must correspond to just a rebalancing here, sort of Markov equivalence. Okay, and now the point is that this copy is associative, so I can also put it here instead. And now, if we look at what we actually have there, this subdiagram, this is precisely the thing that we're assuming that appears in our assumption. So that means in here we can replace h1 by h2. And so then just do the same thing again. Yeah, kind of go back, and then that means we've shown the equation here.
What's the name of the S box? Sorry, just the box on the right is not this, isn't it? Is that just a...
So so let me introduce a little bit of better notation. So let's say we call this actually S. And then this thing is S given X, right? Yes. Is it given X or given Y? Given Y, right? Maybe I'm getting it wrong now.
So, sorry, I'm.
Yes, given Y, yeah.
The circled thing, the circled pink thing is playing the role of F up there.
Yes, exactly.
Okay.
Mm-hmm.
And then you're splitting it into conditional and the marginal.
Yeah. And this is the marginal. Already simplified a little bit.
Yeah, could you explain the simplification? Sorry.
So a priori the marginal is this, right? And now, well, one of the axioms of Markov categories is that, yeah, when you delete one of two copies, that just amounts to doing nothing.
Wouldn't in this case S given Y not just be F because we need the rightmost output to just be F of A?
No, I mean, we need to reproduce the correlation also between X and Y, right? So it needs to depend on Y somehow. And it needs to depend on both A and Y.
And probably in our kind of DAG terms, you're kind of using the conditional independence of Z and X given Y when you are doing these.
Yeah, so I suppose there must be some way to formulate this in terms of DAGs instead. Yeah, so I don't want to sort of claim that this is the better way to draw it or anything like that. But more like the point being that this applies in all Markov categories with conditionals.
And that this.
Yeah, what I think is, because we use a different terminology for causal, I think what you're saying is more like what we would say this category can be causal. Like, for us, when we say causal, it means when we make interventions, it kind of matches with what we have seen. We just make a local change to the distribution. And for some model to be causal, it kind of has to work under these interventions as well, which is, I think, a little bit different from what you're.
Yes, yeah. I mean, totally different. Again, I don't want to claim any relation between this concept. It shares just the same term, but that's just, I guess, unfortunate now. But how
you could say like a DAG can be causal. Doesn't mean it describes the real world causal distribution, but it can be turned into a causal model.
Then what does it mean?
This means that we can at least mathematically imagine that there is a causal distribution under other interventions that there exists that distribution. It doesn't mean it's actual distribution in the real world, because that kind of says the DAG is more than just a probabilistic model. Just kind of want to explore that idea.
Right. Yeah. Okay, so yeah, and any further questions on this, or is it sufficiently clear now? Okay, yeah, then I would turn to saying, some discussion of conditional independence and deseparation. Yeah, this, unfortunately, now I haven't fully finished preparing, and this is, but yeah, so I may not be able to answer all the questions fully satisfactorily. But this is based on the master thesis of one of my students who had basically developed in deseparation in for Markov categories with conditionals. It's proven, the equivalence between the factorization definition of causal model and the local and the global Markov properties. Okay, but yeah, let's talk about conditional independence first. So maybe let me consider the case of morphisms without input first, because then the case of morphisms with input is going to be more subtle, and I think in an interesting way that could be interesting to discuss. But let's start with the easier case that is more clear. And so this would be morphism without input, or so with this domain is this unit object. And so here we have 3 outputs. So and conditional independence then means that we can write this P in a form where the y is generated first. And then x and z. Oh, sorry, I forgot to say this. Here, this was supposed to be saying that this displays the conditional independence of x and z given y if the P can be decomposed like this. By which I mean that there exist morphisms which are necessarily then the suitable conditionals Here, the conditional of basically x given y and the conditional of z given y, and this is the marginal on y, such that this equation holds. So it's basically defining conditional independence in terms of factorization or in terms of the fork causal structure. Yeah, and this is well behaved in any Markov category with conditionals. And I mean, you can prove the semi-graphite axioms and all that purely at the categorical level. You don't need to look at any particular Markov category.
So kind of maybe referring ahead, but so including symmetry of conditional dependence.
Yes, this is obviously symmetric. I'll get to the asymmetric version later, next. This is clearly very symmetric in that. I mean, there's no asymmetry between x and z here. Yeah. So, and because of conditionals, we could also write this as, I mean, using just the factorization, we could equivalently say, well, let's just write it in this form, where we just look at y and z together. And then the x is generated as a function of y only. Or, of course, we could also do it the other way around. So the possibility of decomposing RP in these three ways are equivalent, assuming conditionals.
So just so I understand, this is something you haven't said in lecture, but you said in email, so I'm just trying to understand. So the additional condition that you're getting on Markov category that lets it be symmetric is?
This is still symmetric, and asymmetry comes in when we consider morphisms with input. I'll get to that next.
So you would only define this when you have a Markov category with conditionals.
Right now, yes, but I don't remember. It's only because I don't remember actually right now, and I haven't prepared in enough detail. But yeah, with conditionals, everything is well behaved, right? These are all equivalent. Without conditionals, one can still do some of this, but I just don't remember how much at the moment. Okay, but this makes sense. Does this make sense? That these are, we have conditionals, these things, these decompositions are all, their existence is equivalent. Okay. All right, now conditional independence with inputs, for morphisms with inputs. This is the more subtle case and I think more interesting to talk about. So now let me call this F. So then we say that this displays conditional independence x and y given z and a So we are, at least in this version of the definition, always conditioning on the input, on the input variable. And again, yeah, the definition is in terms of certain decomposition. And again, we can write it in several equivalent forms, assuming conditionals. So one form would be like this. And somehow the important thing here is that the z can directly depend on the a, but any effect of a on x is mediated through y. So let me now use conditionals here in order to also decompose this thing and then draw the corresponding DAG. So this would equivalently be, we first generate y, right? But we also need to copy the value of a here. No, sorry, the wrong way around. Should go to z. Right, so we say that a conditional independence holds if it can be factored into this form. And in terms of the DAG, this would be, and here we have, if we ignore a for the moment, then here we have the fork again, right? And now if we take the a into account, it's only the y and the z that can depend on the a.
Sorry, in your original fork, wasn't it that x and y were the ends of the fork and z was the...
Oh, sorry, am I getting the variables mixed up, the names mixed up? No, y is the center of the fork.
Wait, why does that graph has this conditional independence of x and y?
Oh, I see, you flipped around, I see. Over there you were talking about x independent of z given y, here you're talking about x independent of y given z.
Oh, yeah.
Okay.
Hold on. It's s in.
Oh, sorry, no, this is this was supposed to be the same still, just with the additional, yeah.
So just on that or, so are you saying, yeah, there's an ambiguity here, right? Are you saying if either decomposition is available, we have conditional dependence?
No, these two, if assuming that I've drawn this correctly, they should be equivalent. Again, the existence of these should be equivalent by the existence of conditionals, because you just factor this thing into first generating y and then generating z. So basically, it's just the same thing as here. The existence of these three is, these are all equivalent. And there's another way to draw it. Again, using a Markov equivalence. So which turned out to be like this. I don't have the relevant string diagram written down right now, but if you just use conditionals the other way around, then it should result in and a string something that corresponds to this causal structure. So yeah, I was wondering if, let's say, either of the, so sorry, I was gonna denote input variables like this. If either of these, if maybe some of you had worked with either of these causal structures before, then somewhat reminiscent of the instrumental scenario, at least very superficially. Yeah, but of course then the latent, if we think of A as latent, then it's on the wrong end.
I have a naive question, like, what happens, I guess, in a DAG, if you were to add the A to X, you would still have X independent of Z given Y and A.
So sorry, say that again.
If you introduce A to X, at least in a regular DAG, you would still have X independent of Z given Y and A. So
Yes, so this is the sort of thing I unfortunately cannot answer right now, but yeah, hopefully, let's say one of these days I just have to remind myself of that. But yes, so there was a reason for why we wanted this version, and also this was not our original insight, but actually goes back to a 2021 paper by Patrick Fauré. He had called it transitional conditional independence. Looking at conditional independence for Markov kernels. And yeah, he had then developed corresponding versions also of deseparation in his measure theoretic setting.
Does it make sense here to say X is independent of A given Y? Can A be a part of the...
I think so, but let's say, not according to this definition, but I would have to look it up again,
So the connection to Fourier stuff is sort of useful to know. I mean, I would say, just as a comment, he hasn't, to my knowledge, ever produced an example to show that he makes a compelling case for not having conditional independence be symmetric. That's not for want of asking for such examples. So, and in fact, my understanding of his theory is that if you're interested in variables, that there is a version of his theory where you don't need that extra generality. So essentially, as long as you're working with variables, then it's possible to recover symmetry. So
if as long as everything has the distribution.
Yeah, I mean, I think more weakly than that. I think even without everything having a distribution, that it's if you start wanting to consider things that are not just projections of variables that you run into difficulty. So, yes, I'm just speaking personally for myself. I think the motivation of that approach by Fauré is, I don't know, I would say thin. Let me just put it like that.
Yeah. So for us, I mean, this came up. I mean, we had tried to prove a deseparation criterion using a symmetric version where there was this additional thing here that was allowed, but we were just not able to do it, and it did not seem to be correct. But then, my student realized that if we use this asymmetric definition, then it works. And I suppose, so I would have to remind myself of what exactly the problem was, and then I could hopefully produce an example of that may or may not be convincing. I see, okay. Yeah, well then, sorry, I wish I had an answer right now, but I'll try to look into that.
So he has lecture notes where he's going through the do calculus, and it makes everything sort of twice as complicated because he has to redo every proof with conditional dependence in both directions. And so from a kind of, if your goal is unification and higher level thinking, in my opinion, getting rid of symmetry for conditional independence is not going in the right direction.
Yeah, if you really need both versions of all statements, then that sounds a bit, yeah. But my hope would be that you only need one version of most, that you would only need one version of most statements. Like for this operation, obviously there is a clear asymmetry between the parents and the non-descendants. These are just two pretty different things, right? But yeah, I don't have a really convincing example at the moment.
So this is a definition. And so you're giving this name of conditional independence. Is that because it corresponds to the probabilistic notion of conditional independence and under like Finstock or Stock?
Well, the usual probabilistic notion would not consider input variables, right? Would correspond to this one.
Well, the stuff you're conditioning on could. I would think that the stuff you're conditioning on could go. Doesn't have to have a distribution.
Yeah. Then I suppose the most natural thing you would write down in that case would be the one where this is allowed, and so then no, it would not. This would not correspond to that. But yeah, this I can look into that again and provide more details some other time. But this does seem to be the version that's needed for deseparation in the case of causal models with input variables.
Okay. I'm pretty, just to be laid out, I'm pretty skeptical about that as a case.
Yeah. Okay.
Like the necessity part.
Yeah. I mean, I think basically the idea that we have to give up on conditional symmetry, conditional independence is, I don't know. I mean, maybe it's.
So Thomas, is this related to the extended conditional independence you use?
Yeah, I mean, yes, it's also related to the things that Phil filled in has the extended conditional independence.
But he would write the input, the deterministic thing, as part of the
conditioning set.
Conditioning set and the things that could be dependent of, right?
Yeah, the right-hand side, right?
Yeah, the right-hand side. I mean, basically back to the comments that were made here, this question about can you always write a probability y given, I guess it would be probability of z given x, y, a is the same as the probability of z given y and a. And that's sort of the way, and you don't necessarily, because every statement is conditioned on all of a, then I don't want to derail the discussion, but I would say basically,
Maybe we should see the separate.
Yeah, for me, I think it would be better to look into it myself some more before talking about it further. Okay, so the deseparation, so this I actually have prepared now only, because it was then ended up being a little short on time, only in this case, where you have no input variables, and so then I guess, okay.
Yeah, right, you always stay on time.
Yeah.
Okay, so, and to write that down, let me first say a bit about the relation between string diagrams and DAGs in general. So, I mean, I've already drawn a bunch of DAGs or some, so what is the precise statement? So first of all, given any DAG, we can have input variables as well. We can have some variables specified as latent variables. We can translate that into a string diagram. And well, then that is, I guess, fairly straightforward. For example, as far as the copies here are concerned, you need sufficiently many copies that is given by the number of outgoing arrows. +1 for an observed variable, because for an observed variable you want the corresponding wire to also be an overall output.
Can you think about it as some kind of dual that in DAX your vertices are the variables, these types, the types, and here your boxes are the edges in the DAX, and then the strings are...
Yeah. Yes, but I mean, string diagrams are still more general in a number of ways that I'm gonna write down now. But I think they are, if you have additional decorations for latent variables and input variables, then I think the string diagrams are equivalent to factor graphs. But yeah, I would still want to really prove this formally. This hasn't been done yet, but that seems to be the case.
Wait a second. Were you asking about factor graphs? Or?
I haven't studied factor graphs actually, so I don't know. I just thought, I always felt there's two ways of thinking about causal effect. One is kind of thinking about the effect of a single variable, but the other is also to think about the edges, is the thing that you're making interventions on, which is related to mediation analysis. So it seems that this is providing a language to think about that.
But Tobias, you were talking about specifically like factor graphs, the ones that you use for error correcting code, loopy belief propagation, error correcting codes. Is that was what you meant?
To be honest, I don't actually know what they're used for.
Okay. But you meant separate from DAGs like this. You meant factor graphs, things where you have a node for each term in the factorization.
Yes.
Okay. Right. Okay. I just wanted to check because you suddenly brought that in.
Yeah, so a string diagram corresponds to a DAG. Let's say now a DAG without, well, okay, we can do it in two versions, depending on whether we allow additional decorations for input variables in a DAG or not. If we don't allow it, then of course the string diagram cannot have global input wires. And I'm going to restrict to this case from now on with no global input wires. And then the really important thing is that every box has exactly one output. One output wire. So this corresponds to what I had said at the beginning, right? That we can always use conditionals in order to factor any morphism with any number, if we apply conditioning repeatedly, with any number of output wires into a diagram containing boxes of single output box only. And finally, every wire is a global, okay, so corresponds to a DAG. And so what I mean by a DAG here is no latent variables either, right, since I'm heading towards the deseparation criterion, so that's the case of interest. So no latent variables means that every wire is a global output in exactly one way. Exactly once. So in the sense that we copy so yeah, for example, the y here, the y kind of appears all the way through here, but it's an input, it's an output, also an output wire exactly once. We could also do some silly things and just sort of put an additional copy here, and then it becomes an additional output wire, and so then now it's an output wire in two ways. But this is kind of pretty stupid, right? Because it always gives us the same value that flows on that wire. So that's what I mean in exactly one way. And yeah, we can see this in the causality axiom diagram right here. This is the case. This corresponds to a DAG, but the one wherein the other equation where there was this was not copied, then this x here is not an output wire in any way. So this corresponds to a latent variable and therefore does not conform with these requirements. Okay, so then we can talk about any Markov category with conditionals. And any, well, yeah, now let's say a DAG. We already start with the DAG, and we can translate it into a string diagram. But, well, just to state the theorem, I guess we don't even have to. But, so let's say the vertices are, we call them x1 to xn. And now I want to say, basically consider a joint distribution. So a morphism from the unit object to the tensor product, and consider under what conditions it can be decomposed in the form that is given by the string diagram. And the string diagram is precisely the factorization definition of the causal model. So the following are equivalent. Well, from here on, it's basically just the usual, the kind of textbook statement. But the point being that this applies not just in discrete probability, but in any Markov category with conditionals. So automatically applies to measure theoretic probability of stand-up Borel spaces, etc. Yeah, so P decomposes as in a way that is specified by the string diagram that corresponds to the DAG. So that's the factorization definition. And then, well, we have the local and global Markov properties. Just in the usual form. And I guess this is not really, I guess you shouldn't be surprised by this, because this is ultimately, I suppose we are just using the usual kind of proof of this statement and just translating it into the more abstract language and realizing that you don't actually need to work with these probabilities. All you need is the possibility to do conditioning.
So just one quick comment. So I mean, the equivalence of 2 and 3, people have showed that just from this graphoid axis.
Yeah.
So in a certain sense, so I'm just trying to understand the extra generality here is, where is it?
At the formal, right, what actually was the main difficulty? So yeah, one of the implications was still quite non-trivial, but unfortunately right now I don't quite remember which one.
But I mean, one is stronger, right? I mean, one is a stronger condition than 2 and 3, is it? You could have distribution where there aren't conditions. You could have a Markov category without conditionals, where 2 and 3 would hold, and
Yes, yes. So yeah, then it probably was from 2 and 3 to 1, where we still had to do some work with the combinatorics of the diagrams. But yeah, I mean, I'm not claiming that this is somehow particularly deep or anything. Just that the point is that this applies, for example, to measure-theoretic probability in a way that you don't need to actually mess around with the measures in order to prove it.
So just a clarification question. Are you assuming the string diagram for this Markov category is a DAG?
I'm assuming that it corresponds to it. Yeah. Yes. Obviously, otherwise we could have latent variables, etc. Then this doesn't work.
And when you said P decomposes as specified by the string diagram.
This is the factorization definition of causal model. Interpreted then, I mean, which makes sense in any Markov category, right?
Okay. So you're talking about that morphism decomposing.
Yes. So it decomposes in C, in the Markov category C, in a way that is specified by the string diagram, and under the assumption that conditionals exist, the local and global Markov properties are necessary and sufficient.
So partly I'm playing. Phil David was in the lecture last week, and I'm kind of playing the role of Phil David here a little bit because he would say well, meta-theoretic probability establishes the graphoid axioms, and then from the graphoid axioms we can show 2 and 3 are equivalent.
Yeah.
So.
Yeah. I totally agree with that. But then I did heard about the equivalence with 1. I mean, I think that was the difficult part.
But so usually that's stated as where there exists a density with respect to a product measure. So I guess I'm curious about, do you have examples where there doesn't exist a density with respect to a product measure where one holds?
Let's say I'm not enough of a practitioner to have examples that would clearly be of interest, or to know what kind of examples would be of interest.
Because I mean, in some sense, your conditionals exist condition seems to be, sort of sounds a bit similar to the exists a density with respect to.
No, I don't think it has. I mean, it's sure. Let's say if you can work with densities, if you have densities, and sure, yeah, then conditioning is easier than in a general measure theoretic setting. And so I guess in this case, this doesn't buy you very much.
Okay, but you think there are cases where there isn't a density with respect to a product measure, but conditionals do exist?
Yes, sure. I don't know how, let's say, how relevant those are in practice, but just mathematically, yes. Yeah, because our conditionals correspond to regular conditional probabilities in a measure theoretic terminology, with the additional subtlety that there can be an additional, that can depend on this additional input, have an additional input parameter, and then a conditional, you have to keep track and make sure that it still depends, the conditional, regular conditional also depends on that parameter in a measurable way.
So can I understand this theorem as kind of giving us all the axioms that we've actually used in proving these equivalents? Because in the usual case we can prove it, but it's just some of the things it was not clear if it's you're basically axiomatizing that proof, right?
That's a nice way to think about it. Yeah. That Markov category with conditionals is, suppose, something like a more or less minimal framework in which one has this equivalence. Okay, so now I can finally say a little bit about how to formulate this operation in a global Markov category in terms of string diagrams, if that would be the last thing, if that would still be of interest. Which is kind of independent of this theorem, right? Because whether you use string diagrams or DAGs is independent of whether you work with Markov categories in general or with discrete probability. Okay, so yeah, let me actually start with just a fork and a collider as examples, and then at the end I'll write down the general procedure for the d-separation. Okay, so suppose we have A, C, and B. And well, now we could ask, are A and B marginally independent? And what we do in order to answer this question in the string diagram framework is, well, first actually marginalize C. So then we are left with this diagram. And this is connected. This diagram is still connected. So I'm and then per our d-separation criterion, which I haven't written down yet, but what you need to look at in the end is just the connectedness of the diagram. And so this is connected, meaning that here we do not get the independence of A and B. Yeah, so the diagram that I'm going to be writing down and that I'm using here, it feels somehow similar to doing demoralization. But yeah, again, I haven't gotten around to really comparing them in detail. No.
Actually, this for a fork in moralization, you wouldn't drop C, so it's maybe not quite.
You wouldn't.
But he's not adding something. You're going to add something when it's the collider, right?
No, I'm not going to add anything. Yeah, I'll get to the collider.
Sorry, maybe I'm slow. Why is this a fork? Can you explain?
Oh, because this corresponds, is the string diagram version of this stack. Since that here we first generate C, and then A, A is kind of used in C as input, and likewise for B. And now what about the conditional independence of A and B given C? Well, what we do in order to detect conditional independence is that we remove all the wires that we condition on. And that is importantly different for marginalizing. Because what it means to remove a wire is, so here what I mean by wire is that it is not the thing up to this copy here, but it propagates across the copy. And so the removal of C leads to this diagram. And now this is disconnected. And hence, per the string diagrammatic d-separation criterion, it results in A independent B given C. Okay, for now let's do the collider. The collider is a bit more, laborious maybe to draw in as a string diagram. So here we have A, and then C, And then the B depends on both A, or can depend on both A and C, right? So we have to, for the box that produces B, have to use A copies of A and C as input. Sorry about that. Yeah. Okay, now same procedure. So let's check the marginal independence. So we marginalize C. And here the important point is that when we do this, so apply the deletion morphism up here, it propagates across this box. Because this, I mean, is then one of the axioms in the Markov category. Or so a consequence of the axioms. And so this actually results in this string diagram, which is disconnected. So here we conclude that marginal independence holds. On the other hand, when we remove C, right, so if we're testing the conditional independence, that means we just remove all the wires that we're conditioning on, but removal does not propagate across the boxes. So yeah, this is then what it looks like when we remove that C, and because this is still connected, we get that the conditional independence does generically not hold.
So yeah, so that's the moralization step, right? Yeah, the little box is doing the moralizing.
Okay. Yeah. Mm-hmm.
So question, does this help you construct, in your first talk in the workshop, you basically used reasoning to come up with examples of inequalities. So does the proof for the diagram help you to come up with a way, for example, to show, if you wanted to prove completeness, if we wanted to construct distributions that violate the independence, would that give you a way to do that?
What inequalities did I?
So you use the inflation technique.
Oh, yeah, sure, yeah, right, yes.
So that's a case where you take the string diagram and you want to use it to construct an example distribution. So if your theorem up there is about when you get independence, but basically people have gone through and laboriously done completeness proofs for sort of different state spaces. So like discrete Gaussian, etc. So does the string diagram give you a way to find, if somebody said, prove to me that this is complete, prove to me that for this particular category?
That's an interesting question. I don't know, and so far I'm not aware of anything like that. I think this would still need more machinery than we have so far. But yeah, thanks for the suggestion. That sounds like an interesting problem.
So one more question: if I ask you to test A independent B given C in a general graph, you've got an initial step where you're marginalizing everything else that is not an ancestor.
Yes. Sorry, I was going to write that down right now. I forgot, but yes, yeah, exactly. So the general categorical, string diagrammatic deseparation test is, you marginalize over everything that does not appear in the conditional independence you're asking about. You remove, then in a second step, remove all the wires that you're conditioning on.
It has to be remove everything that isn't an ancestor of A, B, or C, right?
No, I think it's different
No.
because here, like, he did marginalize over C, where C is an ancestor of A and B, like in the fork.
Oh.
That's where it's a little bit different than moralization.
Because you don't lose it, it's still there when you marginalize.
Yeah, it's more like a latent projection because he connects A and B after marginalizing C.
Yeah.
But you might condition on C later, right? So, I don't know if it is.
But you only marginalize the things you don't appear in your statement.
I see.
Okay, yeah, this is what I've had to say. Yeah. So thanks for coming.
Can I ask one more question about the how you determine whether A and B should be connected? Is that, do you have to like do it recursively or something? Like if you have a long path between A and B through
Connectedness is just topological connectedness.
But in your example over there on the right, so
This one?
yeah, so
Right, so here there is a path, and it doesn't matter whether how many times you go back and forth or whatever. It's just about just the topology. So that's one thing I find nice about it. It's and in the end, it's a purely topological criterion.
can it go through a box or not?
Yes, it could. That would have to be a more complicated example, but yeah. I would have to think for a bit what a good example would be.
Yeah, so it could go vertically through a box.
Mm-hmm.
This is basically corresponds to you marginalize to the variables that appear, then that could be an ADMG. Then you would remove the conditioning variables, which means that you do the augmentation, and then you just check over there.
Yeah, makes sense.
It would be our
Okay, yeah, thanks.
way of thinking about it.
Yeah.
Yeah, I guess if we were testing is A independent of D given a descendant of a collider. Sorry, is A independent of B given a descendant of a collider between them? You would first marginalize the collider, move D up, and then you're connected to the box there or something.
Yeah, so just to extend your example a wee bit, if you take the example you had before, supposing you had A, B, C, and D, supposing you have C has a child, but the one on the right, that one, that one. So the graph you've got there, A, B, C.
Yeah.
So if there was a child D,
Yeah. Mm-hmm.
and then you're conditioning on D.
Yeah.
So I guess the question, the thing which would worry me a little bit is if you're just deleting everything other than, if you're deleting all of the things that are not A, B, or D, then have you got rid of the box that had C in it?
Yeah, could you tell us?
No. So if we now marginalize C here, then we just end up with this diagram. So now C is kind of still there if you want, but it's latent.
Yeah, it truly is like latent projection, basically. Yeah, I guess they have. Yeah, it's like a rule. Okay.
Can you? I think one way one thing this could be very useful for us is to formalize causal identification. How would that look like? Can you speculate?
Yeah. No, at this point, I'm sorry. Yeah, but I mean what I want to look into next. Yeah. Yeah. I haven't gotten around to even properly preparing for this.
Formalizing a graphical rule.
I think it'd be really interesting to know if either there are Markov categories where you really need the asymmetric independence, conditional independence, or or if you can come up with a, you can say that you can have inputs without, because I think.
So you've worked on another, what is this called? Someone had mentioned.
Well, extended conditional dependence.
Extended,
That's Phil David did that, and other people have done it. I think it's the dead end. I mean, there are situations where people drop symmetry, like Granger causality. There are situations where they have a specific meaning, but in general, I think, and so I'm being Phil David here. We want to have our semi-graphoid axioms, and I don't want to get rid of symmetry.
So what is extended conditional independence?
It's just allowing input variables. Just allows input variables. You don't have to put don't have to put distribution over it. And sometimes people extend it to allow variation independence. So you might have two input variables, and then you don't have distributions over them, but you sort of, if the set of values they take exists in as a Cartesian product, then you say that they're independent, even though there's not a distribution over them.
Okay. So yeah, I may get back to you then on that if that.
One way or the other, if there was a really compelling example where you needed to drop it, that would be great. Or if we didn't need to drop it, that would also be great. But the situation we're currently in is Flore is telling everybody to drop symmetry, and then there's no motivation example, which I think is kind of not great. I don't mind going on the record with that.